Welcome listeners to another lecture on the subject fundamentals of geology. So the next topic, that is plate tectonics, is obviously an extension or a continuation of the earlier lecture on continental drift. Okay, so now we'll look at a simple animation again, where you can see that the mid-oceanic ridge is spreading and along the mid-oceanic ridge continuously as well as symmetrically you are generating new ocean floor basalt over a span of 2 million years, and due to the magnetic reversals within the earth, there are some zones or some magmas that will possess your normal polarity, and there will be also time when your magma will possess a reverse polarity. Okay, so after this animation again, you can also see a different animation of a subduction zone, but before that we'll refer that the surface plates bend and descend into the interior of the earth is obviously the process of subduction. We have seen the process of mid-oceanic ridges where your new ocean floor basalt or new oceanic lithosphere is getting created, as well as the process of destruction of older ocean floor basalt is going on at the subduction zones, also referred to as convergent plate boundaries. Like for mid-oceanic ridge system, they are referred to as divergent plate boundaries, and for subduction zones they are referred to as convergent plate boundaries, because your oceanic lithosphere is converging onto a different oceanic lithosphere or a continental lithosphere. So that's why they are referred to as convergent plate boundaries. Again, this is an animation where you can see that the oceanic floor is getting subducted beneath the continental lithosphere along the shelf of the continent. So there is a trench that marks the shelf of the continent where your ocean floor is getting subducted, and due to the melting of the subducting slab or the subducting oceanic lithosphere, your new magmatism or volcanism is also taking place on the edge of the continent, which is also referred to as continental arc system. So we'll look into this animation. So now there is a different animation again where you can see that a plate, for example here it is your South American plate, where you're on the west coast of the South America, your subduction is going on along this trench where your Nazca plate is getting destroyed along the western margin of South America, and how with respect to that again on the eastern coast of the South America, your mid-Atlantic ridge is developing in between the South America and the African continent. So here there is a parallel scenario you can see and compare as well, this animation, that where your subduction is going on at one end on the western coast of South America, and your mid-oceanic ridge system is developing along the Atlantic ridge on the far east coast of South America, that is between your South American margin and the African margin. In between there is your mid-Atlantic ridge. So now I can say that this South American and part is actually obviously a plate, because on one side, on the western side, it is bounded by a subduction zone where there is the presence of the Andes mountain belt, and on the eastern side there is the mid-Atlantic ridge system. So a plate will be invariably bound by a mid-oceanic ridge on one side and subduction zone on the other side. So we'll look at this animation again. Okay, so coming into apart from the mechanism that is driving in the plate tectonics, as we have discussed on the mechanism, that is mainly the presence of the convection cells that are operating within the asthenosphere, and how the convection cells are driving the lithosphere to into the formation of a divergent plate boundary, leading into formation of mid-oceanic ridge system. Also, we have seen how these convection cells are driving the older oceanic lithosphere to bow down between continental lithosphere or younger oceanic lithosphere, forming the presence of convergent plate boundaries. So broadly, just to look at the different types of plate boundaries, you can have divergent plate boundaries, then you can have convergent plate boundaries, as well as you can have strike slip plate boundaries. In case of strike slip plate boundaries, there is a very interesting thing to mention, that in case of strike slip plate boundaries, there is neither destruction or neither nor there is any generation of new oceanic lithosphere. That means plates are only moving past one another, or they are sliding past one another. So there is no subduction to consume, or there is no evolution of or new oceanic floor material is not being created at your strike slip plate boundaries. So this ternary classification scheme shows the three end members of your strike slip plate boundaries, divergent plate boundaries and convergent plate boundaries. Sometimes there are a few examples across the earth as well, where you can see a combination of strike slip and convergent plate boundaries, which is categorized under transpression boundaries. Then you can also have divergent and boundaries combined with strike slip boundaries, which are considered under transtension dominated boundaries. And also there are some, a very few, but there are some syn convergence extension that has been recorded on the earth as well. So these are the three end members or three broad types of plate boundaries that you can see on earth. Again, strike slip boundaries, where there is no construction or destruction of ocean floor material. Then you have divergent plate boundaries, where there is always generation of new ocean floor basalt or new oceanic lithosphere, as well as there is subduction or convergent plate boundaries, where there is always consumption or destruction of ocean floor basalts. Now, if I look again at the global arrangement of different plates, like I was mentioning a few, like this area marks the Andes mountain belt here, where your Nazca plate is getting subducted beneath the South American plate, as well as here you can see the presence of this Atlantic ridge, mid-oceanic ridge, where it marks the easternmost boundary of the South American plates. So again, to define plate, if I say that the plate is invariably bounded by this subduction zone on the western side of the South American plate, as well as this mid-oceanic ridge system on the eastern side of the South American plate. Similarly, if I look at the Pacific plate, which is obviously the largest plate on earth, so this Pacific plate is getting subducted along the Japan Trench, Philippine Islands as well, and then you have this Aleutian Trench. So these are all the bounding margins of the Pacific plate, which are subduction zones, as well as here just on the other side of the Nazca plate, this whole part is your Pacific plate, which is the western part of the East Pacific rise. So your East Pacific rise is again the mid-oceanic ridge. So your one end you have subduction zones, at the other end you have mid-oceanic ridges, and this mid-oceanic ridge, your East Pacific rise, separates the Pacific plate from the Nazca plate, and this will refer to as a divergent plate boundary. Similarly, the boundary between the Nazca plate and the South American plate will refer to as convergent plate boundaries. And now the most important feature, you can see small displacements all along the trend or all along the length of the mid-Atlantic ridge like this. Also, you can also look at the East Pacific rise here, where you can also see certain offsets. This is not a continuous line, also this is not a continuous line, means there are smaller offsets across the length or the trend of the mid-oceanic ridges. So this smaller offsets are actually nothing but getting accommodated, or these offsets are your expressions of your strike slip boundaries between two plates. So here you can see you are not generating any new oceanic lithosphere, you are not consuming or destructing any oceanic lithosphere. So these strike slip faults, they are here just to accommodate the relative displacement across a mid-oceanic ridge, because all along the length of the mid-oceanic ridge, the relative velocity of the plate are not always same or not always constant. So that's why you need these strike-slip faults which can accommodate these minor changes in your relative motion among the plates. Now, just if we take an example and if we try to solve this simple question, that if a plate X moves to the east and a plate Y moves towards west, then what type of plate boundary would you expect? So, if I simply write or if I simply try to draw that if a plate X is sitting here and again you have a boundary between this, obviously there are two plates, means there has to be a boundary in between them. So, what type of plate boundary would you expect here? So, if your plate is moving towards east, if obviously if I take this one, the upper side as north for our understanding purpose, then if your plate X is moving towards east and plate Y is moving towards west, then what kind of boundary you might expect? Obviously, both the plates are converging on one another. That means you will get to see a convergent plate boundary. It depends again on the density, relative density of X and Y, that whether that X will subduct beneath the Y or Y plate will subduct beneath the X, and that's a different question. But this boundary will always give you a convergent plate boundary. So, here what I am showing that Y has a relatively higher density, that is why I am putting this small teeths or dents on the X side, which marks the overriding plate of a subduction system, and Y marks the undergoing plate or underlying plate of a subduction system. So, in this case, when your boundary is aligned parallel to north, this scenario will give you a convergent boundary. Now, if I just change this scenario with the same orientation, but here now I am putting Y here and X on the right side. But again, if I apply the assumption that X is moving towards east and Y is moving towards west. So, this will give you what? Y and X, they are moving away from each other. So, definitely what you will get a divergent plate boundary, that the plates are diverging from one another. They are not converging like the earlier example. So, just by the if I am changing the arrangement, when in the first case where I have kept X on the western side and Y on the eastern side, you are getting a convergent boundary. With the same two plates, if I only change the position, that I have kept X on the eastern side, I have kept Y on the western side, you are getting in the second case a divergent scenario. The first one is a convergent. Again, if I place X and Y in such a manner like this, where X is placed in the northern half with respect to the Y and Y is present on the southern half, then also I can think of the movement of X in east and movement of Y in west. So, this third scenario will give you a strike slip dominated plate boundary. So, these are the three plate boundaries you can always think of with the same arrangements of the plate, but depending on the movement of the plate, on which side your plate is moving, will give you the condition whether the plate boundary will be divergent in nature, whether it will be convergent in nature, or it will be strike slip in nature. Now, before I finish this discussion on plate tectonics, one very important finding that I would like to share is by Wilson. Wilson came up with a very interesting idea of which is referred to as supercontinent cycles, or also sometimes referred to as Wilson cycle, as it was hypothesized by Wilson. So, what he proposed, that at every subduction zone your older oceanic lithosphere is getting destroyed or getting consumed along the margin of a subduction zone, and your new oceanic lithosphere is getting generated or getting created at the places of divergent plate boundaries, which are referred to as mid-oceanic ridges. So, he came up with this idea that at the margin of the continental shelf, where you get to see the oldest oceanic lithosphere, that is why they are getting subducted. The age of this oceanic lithosphere is more or less around 250 million years. It is never more than 215 million years. At times it is even low as that of 180 million years, but dominantly they are above 200 million years till 250 million years. So, Wilson proposed that if the oldest ocean and floor lithosphere or the oldest oceanic lithosphere is of 250 million years, then it is possible that the first supercontinent that formed it evolved into a divergent boundary like this. If there is a supercontinent somewhere in between, if I just take this marker, so this is your first supercontinent that you can see. It's obviously it's a cartoon form. Supercontinents are not as uniform as this, but you can simply relate with this. So, after the initiation of rift system, that we have seen the initiation of rift system in Rio Grande River or the Great African Rift. So, there is an initiation of a rift system within the supercontinent, then it started to diverge from one another. So, there are three divergent plate boundaries like this, where each of these three plates are moving away from each other, or three continents are being separated by the formation of the linear oceans in between, that we have also seen some global examples of linear ocean like that of the Red Sea. So, you are generating these divergent plate boundaries where your continents are moving apart from one another. Again, it will go to a distance where in the margin of this continent you will get the oldest age of the oceanic lithosphere, that is about your 250 million years. So, as the ocean floor grows old up to near about 250 million years, again this margin, these continental margins that are present along the margin of the oldest oceanic lithosphere will now get transformed into convergent margins. Why? Because obviously the 250 million years old oceanic lithosphere is the oldest as well as the most dense ocean floor material that we can find on Earth. So, now that same ocean floor will now, that was separating the continents away from each other, will now again take the continents, or will compel the continents to move towards each other. Why? Because again this ocean floor that are present here like this, these are the divergent plate boundaries. Now, you have the oldest ocean floor at the margin of the continents like this, and now these margins are getting transformed into subduction zones. All these margins are getting transformed into subduction zones. So, there is destruction of this oceanic lithosphere that was sitting in between these continents, this oceanic lithosphere that was sitting in between these continents. So, now this oceanic lithosphere is completely getting consumed. So, as the process goes on, so to destroy again the 250 million years old oceanic lithosphere, you need another 250 million years to destroy the ocean floor lithosphere completely. So, this process, this separation and union of these continents will take a 250 plus 250 million years time, a total of around 500 million years time to complete this cycle of your separation of continents as well as union of continents. So, this whole cycle of supercontinent separation and unification takes a time of 500 million years. So this was proposed by Wilson, and now if I look back at the early Earth system, when possibly when the plate tectonics phenomenon started, it was around 3 or 3.5 maximum billion years. So now if I take the supercontinent cycle into consideration, that one cycle will be of 500 million years, then in total in a history of 3 or 3.5 billion years, how many supercontinent cycles are possible? Obviously maximum 6 to 7. So there has been a proposition by Tujo Wilson then that we have been through maximum 6 to 7 supercontinent cycles across our geological history of around 4 to 4.5 billion years. So there are maximum 6 to 7 supercontinents that have been present on the earth, no more than that. It is not possible to have more supercontinents, more than 6 or 7 in total. So now just to remind you of another point that is very important, that always remember that the movement of the plates are not uniform throughout the earth. It changes from time to time, as well as it both changes its direction as well as it changes its magnitude. Means the amount of movement of the plate also varies from time to time. Also the direction of the movement of the plate, it also varies. So this animation again shows a very distinct way to represent that how plates are moving for the last 200 million years. So look into this animation. So coming back to this, I will simply end this with a simple movie poster from the movie Ice Age. So here you can see that how your continents are drifted from one another, and on the two sides of the continents there are different species of animals that are getting separated, but they were actually together at some point of time. So with this poster, I would again like to remind you that Alfred Wegener was actually right, that continents do drift from time to time, but obviously the contribution of Hess and Arthur Holmes was also should be taken into consideration, because they actually explain that how your continents drift. So with this note, I would like to end in this discussion on continental drift and plate tectonics. Next we will come up with the discussion on minerals and rocks in my later lectures. Thank you.